Welcome to lecture number 35. So, in the last lecture we are discussing about this excited state proton transfer, and today I would like to show you how to find out the rate of this kind of excited state proton transfer process. To start with, let me take a very basic model of a two state irreversible proton transfer process. So, let me write it over here. I have this HA star which is converted to A minus star because of the removal of a proton from it. Let me write this rate constant here as a K1, but this you do not forget that this H star has its own radiative rate constant, right. So, or the deactivation rate constant, which I altogether termed as Kf over here, and this one I termed as Kf prime. So, then with this rate constant it will form the ground state of HA, and with this rate constant it will form the ground state of A minus. So, my whole model for this excited state proton transfer from H star to A minus star is like this, with the three different rate constant Kf, Kf prime and K1. Now, if I write these rate equations over here, I can write minus d H star dt is equal to the two pathway, right. One is K1, another is Kf, right. So, I will just write K1 plus Kf, all are small k, do not confused with the capital and small capital K, here is the small k. Okay. K1 plus Kf into concentration of H star, and I can also write the formation of this A minus star, right, like that way. So, d A minus star dt, here K1 is the formation and the this Kf prime, this one is the decay, right. So, K1 to HA star minus Kf prime into A minus star, right. So, let me name this as equation 1 and this let us say equation 2. So, from equation 1 what I can write, is minus ln H star, right, is equal to K1 plus Kf to T plus C, right. Now, I will put this boundary conditions over here. So, here the boundary condition is at t equal to 0, that means just before the starting at just at time 0 of the starting of the reaction, the concentration of HA star is H star 0. So, it is the initial concentration. So, I will write these conditions over here at t equal to 0, HA star is equal to H star 0. So, I can write this equation as H A star is equal to H star 0 e to the power minus K 1 plus K f into T. So, you see, if you monitor the H star, the concentration of H star will start from an initial value and then it will decay exponentially, and the rate constant is K 1 plus K f, and the time constant will be inverse of this, right. Time constant will be just inverse of this. Okay. Now, let me do one thing. Let me take from the equation 2, and from equation 2 let me write this as d a minus star dt is equal to k 1. This is my equation 2, k 1 h a star, right, and this h star now I will replace with this expression, right. So, I will just write h star 0 e to the power minus k 1 plus k f into t, right, minus k f prime to a minus star, that is it. So, I can take this k f prime a minus star in the left hand side, and then I will multiply the both side with e to the power k f prime into t, right. Let us do that. So, d a minus star dt plus k f prime a minus star is equal to k 1 h star 0 e to the power minus k 1 plus k f into t, and I am multiplying both side with e to the power k f prime into t. So, then this whole differentiation I can write as d dt of a minus star e to the power k f prime into t, right, is equal to k 1 h a star 0 e to the power minus k 1 plus k f into t into e to the power k f prime into t, right. So, from that equation now I can write a minus star e to the power k f prime t is equal to minus k 1 h star 0 divided by minus k f prime plus k 1 plus k f e to the power k f prime minus k 1 minus k f plus c, right. Now, I need to find out this c. I can simply first divide both the side with the e to the power k f prime into t, and then I will put this condition that at t equal to 0 a minus star is equal to 0, just after dividing both side with this quantity. So, this I will divide both side, and then I will write this one. Then the equation what you will get is for c is equal to just this one with the positive signs. So, k 1 is h a star 0 divided by minus k f prime plus k 1 plus k f, and then if I put this value of c in that equation, ultimately the equation what you will going to see is a minus star equal to minus that quantity K1 H star divided by minus Kf prime plus K1 plus Kf into e to the power minus K1 plus Kf into T, then plus exactly the same quantity will come now K1 H star, this should be 0 divided by minus Kf prime plus K1 plus Kf e to the power minus Kf prime into T. Earlier what we have seen? Earlier we have seen this HA, na? H star, how H star was decaying with time, and we got this formula H star equal to HA star 0 e to the power minus K1 plus Kf to T. So, this is the how the fluorescence intensity of H star is changing with time, this one, and this is how the fluorescence intensity of A minus star is changing with time. Here you can see for H star only decay, because this is a positive, right, and this is exponential minus rate constant into T, 1 over the rate constant is your time constant. So, it will start from an initial value and will decay. But in this case, please note here, these two are same, this quantity and this quantity are same. So, this is a special case, right, for the irreversible two state proton transfer. But most interesting thing is that here you have a negative sign and here you have a positive sign. Negative signs, this exponential means the formation. So, first this A minus star will form and then A minus star will decay. So, here is my formation, here is my, this part is my formation, and this part is my decay, and here is my decay. So, that is why people generally do not want to tell the fluorescence decay as in general. We want to say the fluorescence transient, right, because it may be in some case like this case it is not a decay, it is a formation, it is a rise, right. So, generally we speak as a fluorescence transient, right. So, now if I plot this fluorescence transient of HA star and A minus star, right, how it is going to look like? Let us plot it quickly to see that. So, let us say this y axis is my intensity and this x axis is my time axis, right, and this is my fluorescence intensity, and let me draw this HA with the green color. So, here HA looks something like this. This is just a single exponential decay, a nice single exponential decay, right. But this A minus will be, first there is a growth, right, and then there is a decay. Now, you see the for the formation this rate constant and for the decay this rate constant, they are exactly same, right. So, that is why I draw the formation like from here to till over here and then it will start decaying, right. So, this is for the A minus star and the other one is for H star, right. So, from your time result measurement either by TCSPC, if TCSPC is good enough, if this process is slower than 100 picosecond, because your time resolution in TCSPC is about 100 picosecond, but in most of the cases like if you do in the water like 2 naphthol in water, this rate of proton transfer, right, is in the order of 1 picosecond. So, TCSPC is not suitable for such kind of experiment. What you have to do? You have to use the up conversion method, because in up conversion the IRF is around 200 femtosecond, 100 femtosecond, right. So, obviously here the IRF is over here. So, this is my IRF, right, and with this IRF it is visible, right. So, this formation is visible over is my formation. Okay. So, as I told you, this 1 over this is your time constant. So, generally people write this as a time constant. So, we can write that tau 1 is equal to 1 over k 1 plus k f, and tau 2 is equal to 1 over k f prime, and we can write all these time constant from this experimental data. Now, let me just quickly show you that what happens if this is a reversible two state case, right. So, in that case my model is H A star is forming to A minus star, and here is k 1, here is my k 2, and this is as usual is k f, and this one is k f prime. This is making H A and this is making A minus, right. Then similarly I should write those equations to start with, minus d H A star dt is equal to k 1 plus k f H A star minus k 2. This is my extra term which was not present in case of irreversible two state proton transfer. So, A minus star, and I have d A minus star dt is equal to k 1 H A star plus k 2 plus k f prime into A minus star. Right. Similarly, what we have done for this irreversible case, I can also do this for the reversible case, and ultimately this solution will be much more difficult than the previous one, and it is out of scope that I will solve in this lecture, but I would like to show you the result. Ultimately, if you solve, what you will get? You will get the H star, how the H star is changing with time, how the A minus star is changing with time. Those two you will get like in the previous case, and those expression I will show over here. So, H star equal to H A star 0 divided by m1 minus m2 to x minus m2 e to the power minus m1t plus H A star 0 divided by m1 minus m2 is a complicated one to m1 minus x e to the power minus m2 into t. Obviously, I have to tell what is m1 and m2, that I am telling later, and then A minus star will have the form x minus m2 okay, into x minus m1, then H A star 0 divided by m1 minus m2, and then k 2. This is my k 2 over here. I should have this exponential part, e to the power, here it will come as minus m1 t, and then I will get this minus. So, here this minus sign signifies the formation, right, minus x minus m2 into x minus m1 like this way, h a star 0 divided by m1 minus m2 into k2, and this will be my e to the power minus m2 t. In this case, x is defined as k1 plus kf and y is equal to k2 plus kf prime, and m12 is defined as 1 and 2 is equal to half x plus y plus minus root over x plus y whole square minus 4 into xy minus k1 k2. Okay, so now as you can see here, this is going to be a very complicated equation, and but if you monitor the decay of this HA star or the fluorescence transients of A minus star, it is possible to evaluate the different rate constants like K1, K2, Kf and Kf prime. So, you see in this case the equation is little complicated, right, but by monitoring the time resolved emission one can get such kind of rate constant of the proton transfer. So, we will finish and thank you for your kind attention.